Cooley and Tukey. These guys were working back in the day, late 60s, early 70s, rocking it, kicking it, and they were working with computations on super slow computers. So they were looking for any way to speed up the computation that was possible. Okay? So, two really bright guys. They were listening to Hendrix probably, just, rocking out one day, and then going like, hey, wait a minute. Check this really simple observation out. Here is the observation that transformed the power of the FFT. Let's just work it through. Okay? So if I think about this thing being the kernel here, sorry. Yeah, I'm going to give it to you right now. Wn, let's call it JFK, is equal to 2 pi JFK over n. Okay? So we're looking at the nth Fourier coefficient. Right now, take some JFK, but the same here and here. I can keep carrying it around. These are the Fourier. These are going to be integers that take you through different frequency components and different spatial components. So if you so here's what you're going to do. When you walk through, you have different k's and different x's. You're going to discretize k and x to get out. So for instance, if I go to the f of kth component, I fix the k, and then I've got to walk through all the x components.
And there's little n in the right-hand side?
There isn't. Let me come back to that. Okay? For right now, what I want to do is I'm going to replace, sorry, that's the n right there. Okay. Here's what I'm going to show you. If I take this thing here squared, so let's take, and what I'm going to do is for the moment, let's take j and k to be 1 for a minute. Doesn't matter so much, but because I can just take any JFK and this will work. And what I want to show you that if you take this thing to be e to the I 2 pi, right? And now I replace n here by 2n, and then I square it, right? So then it's multiplied by 2 pi again. This is just to show you just what the calculation does. You say, take this thing, 2n, multiply it. That's 2n, right? And what can you do with exponentials? Well, when you multiply exponentials, you add their thing here together, right? So that's what this is equal to, which then gives you half of this, half of that, makes a whole one of those. Hey, but by the way, isn't that the definition of that? Okay? So that's all it's trying to show you. So in other words, there is a relationship between component n, component 2n. That's the simple relationship that Cooley and Tukey honed in on and said, wait a minute, we can use that information. Okay? Now, I'm kind of going to go through this fairly quick, just try to highlight to you the idea of what happens here, because I didn't want to spend a lot of lectures going over this. Okay? But the consequence of this is enormous. Okay? And Cooley and Tukey recognized it right away, that if this is true, then enormous consequences. And here's the number one consequence that comes up from this. The consequence is this. If we think about representing our Fourier transform as something like this, which I had written down over there, which is you take x, you multiply a matrix F, and you get a vector y, which is in the Fourier domain. This is a Fourier transform in sort of its most abstract way of thinking about it. And so here's your frequency components, here's your time components. Okay, so this problem is sized generically, say, n by n. Right? N by n matrix here. And so when you do this, this will cost you order n squared because you have to multiply and add. Okay, you have to go for each row. For each row, you have to do the sum across that row. But here is what this thing implies. There's now, and what makes up the matrix F, by the way? Here's the key thing. What makes up the matrix F are these kernel components. These guys, the omega, W, N, JKs, the frequency content transform components, your cosine and sine basis functions, which, by the way, are related. So when you write out that matrix F, you see that in that matrix F, you have things like omega n, omega 2n, omega, all that's sitting in there, and they're related to each other. So you can take advantage of that. And the ultimate consequence of it is that this problem here can be rewritten. And in particular, if I make two new vectors, xe, or actually four new vectors, okay? X even, X odd, Y odd. And what these are, so X even is X0, X2, X4, all the way to X of n. Y even is something similar. It's Y naught, Y2, Y4, all the way to Y of n. Then X odd is X1, X3, X5, all the way to X of n minus 1. And Y odd is something similar. Okay? So why do I write it this way? Because now, look, what I've done is taken this vector x, which has x0, x1, x2, x3, x4, all the way to x of n. And now I'm going to break it down into two vectors, x naught and xe. So notice I take every other component out here, and then every other component out here. Right? So this big vector like, watch this, ready? Graphical illustration. Do you see that? Wait, see? x0, x1, this little piggy went, anyway. X naught, x1, x2. Did you see that? Kung Fu action right in class. Nobody's yelling yet. Okay, that's what I did here. And the reason you could do this, you can do it anyway if you want. And generically, you'd say, okay, big deal. You wrote two vectors out. But because of that relationship that we just wrote down there, what happens with this problem is the following. This problem here now can be written as this here. Let's put an n there. That's the size of that matrix, n by n. Now it can be written as the following. It can be written as two problems, and they separate. That is what that relationship allows you to do. And it takes a lot of algebra to kind of work it all out. That's why I don't want to get into it in class. I don't like doing a whole bunch of algebra in class. But that's what happens. This problem translates into two problems. By the way, m now is size n over 2. This is the beginning of the Cooley-Tukey algorithm for the FFT. I took a problem of size n, which cost me order n squared, and I wrote it as two problems of size of half the size. All right. Let's do an operation count. This cost me order n squared. This still costs whatever the size of this squared is, but notice, what do I have here? I have two of them now. I have to do that one and that one. And what are their sizes? N over 2 squared. Check it. Oh, look at this. You square n. Oh, that's n squared. We don't like that. But 2 squared on the bottom is a 4, and a 2 up top up there. I left with a half. I just cut this problem size in half. Right? Remember we did that? It's all karate related. Okay? It's good. Isn't yoga like karate a little bit? Except more relaxing, maybe. All right. Everybody get that? That's good? So that's impressive. You split the problem took half the amount of time. You do not have to stop the algorithm here. The relationship allows you to say, we'll take that problem, split it in half. Pull out every other vector. Boom. This can be written as two problems. What are their sizes? M over 2. So all of a sudden you do another step, and you get a factor of, well, I've got 4 problems now. Each of them of size n over 4 squared. Total cost for you today. Special price, my friend. N squared over 4. Now, if you do this n times, what are you going to end up with? Right? You're going to get an n on the bottom here and an n on top. N squared on top. You're going to go all the way down to, this is why you want to chop it up into powers of 2. Because you take a problem that's, let's say, a size 64 by 64, and you drop 2 problems of size 32 by 32, which is 4 problems, 16 by 16, which is 8 problems, 8 by 8, right? 16 problems, 4 by 4, 32 problems of 2 by 2, 64 problems of 1 by 1. So when you solve a 1 by 1, the operation count is basically 1, right? And you put them all back together. So you're going to go all the way down here to cost you order n.
Wait, this is for one dimensional, right? Or
Yeah, so
okay, so
we think of the two-dimensional case as being just reshaped, right?
Okay.
Remember, the two-dimensional case, when we think about the two-dimensional case, you're reshaping one-dimensional, yeah. So you're going from order n squared all the way to order n. This isn't still quite right, because once you do this, you've got to go back and take all these results of these split problems and put it back together. That's going to cost a little bit. And by the way, here's a formula how it's going from here to here. And here's what it does. Y of n, which is what you're trying to reconstruct, and this is for n equals 0, 1, 2, all the way to m minus 1. And then you have y of n plus m is equal to y n e minus, capital N, n, y, n, 0. And this is for n equals 0, 1, 2, to m minus 1. And by the way, here is the genesis of this. Remember when we do the Fourier transform? We plot it in class. We take Fourier transform function and just this. It's right there. So I start off at the 0th component, and I start counting forward, and I take this even guy with the odd guy with this weighting here of the Fourier coefficient. I add them all together. So once I solve this problem and this problem, I add them together from 0 to the m minus 1. M is n over 2. So I get the first n over 2 components, and then I come over to here and says, well, this goes from 0 and n over plus m. Well, that's n over 2. And then that gives me the rest of the components. The shift happens right there. Okay? That is why when you take the Fourier transform, there you are, and you're working in this space. This happens because when you want to come back from this problem, back up to this problem, you have to do the algebra to get you, how did you go from here to here? Well, you did this. Well, how did you go from here to the next level? Then you did that for that problem. In fact, it's called the butterfly algorithm. And let me just show you what it looks like graphically. So, and you'll see why it's a butterfly. Let me draw some lines here, and this is going to be for 8 coefficients. 1, 2, 3, 4, 5, 6, 7, 8. And over here, I'll have y0, y1, y2, y3, y4, y5, y6, y7. Over here, x0, x1, x2, x3, x4, x5, x6, x7. What I want to do is take information here and bring it back up. Okay? How does it work? Well, first, when you go from this problem, what this tells you is how to go from here to the next level, which is it takes these and interleaves them. So these guys here go down from here all the way to, so here we go. Boom, 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 boom. 1, 2, 3, 4. There's your shift. That's just algebra of taking the problem from size n to two problems of size n over 2. Here, in this case, problem size 8 to two problems size 4. But then, I have two problems of size 4. What about this problem of size 4? Well, this problem of size 4 also gets interleaved. Two problems of size 2. Same thing happens here. And I may have done it wrong, but I think that's right, actually. Okay, so what you did, remember, this is about a connection formula. I don't go through it in class because it takes a while to work out just this simple result here. Take this, show that it's these two problems. It's a lot of work to then just derive this. But it's algebra. At the end of the day, there is an algorithm that tells you if you go from here to here, here are the relationships allowing you to, if you solve this problem now, how do I reconstruct the original thing? Here's the formulas. The formulas do this. And by the way, the reason when you look at the FFT, the reason it doesn't undo that is because it costs you time. The whole point is you're trying to save time. Why fix everything up? Because it's going to cost you. The amount of time to go back this way, by the way, log n. So n log n. That's how this thing works. Here's the high-level graphical representation of undoing the algebra. And that's why you see what you see from the FFT. This stuff shifted, this stuff shifted. Boom. Okay, we're going to talk more about other spectral basis later.